I'll repeat all the steps once, this time more specific, and let's take genetic algorithm. Already studied, so a very quick review. Let's say that the fitness function or the cost function, again I'll use both the terms interchangeably, of course. So I say fx is equal to x1 square plus x2 square plus x3 square. Very simple, you know the answer is 0, 0, 0, and x1, x2, x3. So let's say xi is between -1 and 1. So the first thing that I need to do in order to start the reproduction and all this wonderful thing is to have my initial population. So let's say how will one individual gets inserted, and once I insert one individual, then I will make lots of random individual. I'll be the god, I'll make in the initial population, and that will be my initial population. So in this one, I need x1, x2, x3 to be optimized. So finally, I need to optimize x1 value, x2 value, and x3 value. And therefore, I say that let this be the individual. And let's put in random values which satisfy this norms, 0.8, minus 0.1, and 0.3. Now, this is of course an individual, and this is called as an individual in the format that I will optimize. Which is currently a linear array, and this is called as a phenotype, genotype. So you are immensely beautiful, no matter who you are and where you are an immensely beautiful human being, and internally all you have is a number of genes and chromosomes. So all those collection, all those arrays of genes and chromosomes is what is the genotype. Now, along with the genotype, I also have something else, and the something else is the individual in the format useful to the problem, and that's what's called as a phenotype. So let's take in some problems, and let's say what will be the genotype and the phenotype. You are an amazingly beautiful human being, so the human being avatar of yours with all the wonderful capabilities at solving this problem, looking with eyes and whatever goes on, that's a phenotype. If I look at you as a very large number of genes arranged in a characteristic manner, you are the genotype. We'll soon be optimizing neural network using genetic algorithm. So the entire neural network, that Python code, that TensorFlow code, that C++ code, and all that specific object of Python, C++, Java, TensorFlow, whatever, MATLAB, whatever library you are using, that's a phenotype. It's a callable function, it's a class object. But then if I note down all the weights and biases, objects are not optimized, some specific parameters inside that object is optimized. If I note all of them down in one after the other, then that's a genotype. The traveling salesman problem, somebody wants to go and visit all the cities. So the final printout which is given to that person, that traveling salesman, that go visit this place, then this place, then this place, then this place, then this place. So go visit the computer center 1, the admin building, the library. So that printout is what is the phenotype. That's the one that the individual will finally get. But in order to optimize it up, I say let CC1 be 0, let library be 1 and the distance between 0 and 1 is whatever, which is not optimized, that's constant. So the order of visit of places, that 0, 1, 2, whatever, in this linear format is what is the genotype in nature, is what is, of course, the genotype. I'm taking this lecture which is getting compressed by using algorithms which have a lot of parameters. How did the parameters get set? By an optimization function, a similar optimization. So the entire code for the compression algorithm, that's the phenotype, but then the parameters, the encoding of it in the way it is optimized is what is the genotype. Similarly to say, these days the clothes, the furniture, the cars, they are getting designed by genetic algorithms. So the entire car that you drive, that's the phenotype, but genotype is the parameters in that which are getting optimized. So all the curve function of the front bonnet, of the back bonnet, the parameters like the height and the length, that's what's the genotype. For each one of them, you also have a corresponding fitness function. Like for the neural network, you have the standard loss function, which is the mean square error plus the regularization parameters. For the other problem, which is of the design of a car, you've got all the aerodynamics and the fuel economy. From of that, of course, the human comfort factor, otherwise cars will not have any chairs inside them. And of course, for the other problems, you've got in specific fitness evaluation function, traveling salesman problem, the length of the entire tour. So that's the first thing to do. Now, this type of individual where you've got a linear array with real valued parameters inside them, this is called as a real coded representation. And correspondingly, the algorithm is called as a real coded genetic algorithm. There are variants, so that's the first strategy. The second way is a classic binary encoded representation. So I say that I will optimize this up to 4 places of digit. So one, and then you say that, okay, how many before decimal, how many after decimal. So currently I know it's all fractions, so 4 places after decimal. So you need to represent the number 0 to 9999 in binary format. Do the mathematics, find out how many zeros and ones does it need. So this will be the binary encoding for x1. Alternatively, you can say how is 0.8 internally stored in the memory. So there's a characteristic and there's a mantissa. So reserve some bit for characteristic and some bit for mantissa. And similarly for x2 and similarly for x3. So that's a binary encoding. The only problem is you need to find out how many the number of bits for every digit is a parameter. If it's too high, then we'll soon see that optimization has the curse of dimensionality. Extremely high dimensional are difficult to optimize. And if it's very low, then your resolution is not good. That's why we won't be discussing binary encoded representation. Real encoding, we didn't have any such parameter. So this is very hard to set. You set it too high, optimization is impossible. It takes too much time and then also it doesn't optimize. You set it too low, you get great answers, but your resolution is very bad. So the optimal answer was 2.00, well, let's say 0.005891, but you can only either get 0.0 or 0.1 because you only reserve very few bits. That doesn't solve your problem. The third is, of course, a tree representation. So sometimes the genetic algorithms, they solve the problem of generation of computer program very similar to what I've done. What's a computer program? It's eventually some kind of a tree. Arithmetic expression, it's some kind of a tree. So all those infix expression. In fact, machine learning, you need to find out an arithmetic expression such that your loss function over that arithmetic function is optimized. So you need to find out an arithmetic function mx such that summation over all training data, 0 to n training data, the model predicted output, which is represented by this tree. So this is m of x minus its target is minimized plus regularization. The regularization in this term is the number of nodes over here. So it's a tree-based representation. Generation of computer program, it's a tree-based representation. Now this one is specifically called as genetic programming. And if you do not use crossover, if you only use mutation operator, you do not use crossover operator, it's also called as evolutionary programming. Again, this is not a course on evolutionary programming anyhow. We're just using it as a recap of background because I'll develop over it. So we'll not be discussing either a binary encoded representation or a tree-based representation. There's actually another representation, and that is along with xi, which is x1, x2, x3. I also store what is good mutation rate for x1. And mutation rate for x3. In short, we talked that optimization is used also to optimize the parameters of different algorithms. So evolutionary algorithm itself has parameters who optimizes it. So I can have an evolutionary algorithm that not only optimizes the individual but also the parameters inside it. The most important parameter is, as we'll see, mutation rate. So the algorithm parameters get optimized simultaneously to the genes or the chromosomes of the individual. This is called as the evolutionary strategy. So again, it's not a course on evolution, so we'll neither see genetic programming, nor evolutionary programming, nor evolutionary strategies, nor binary encoded genetic algorithm. We'll only deal with the real encoded genetic algorithm.